On behalf of 9 Sigma, I'd like to welcome you today to today's PARC webinar. On your screen momentarily, you will see a polling question. Polling question will be up for a few minutes while we begin today's webinar. If you could, please take a few moments to answer the poll question. We will discuss that at the very end of today's webinar. We'll just wait a few moments while we're waiting for a few more attendees to join. And we'll get started right at 12 o'clock. Thank you very much. All right, well, it is now 12 o'clock, so we'll go ahead and begin. As I said, my name is Jonathan Yaksha, and on behalf of 9 Sigma, I'd like to welcome you to today's webinar brought to you by PARC, the Xerox Company. And as I mentioned previously, you should be seeing a poll question that we would appreciate you taking a few moments to respond. You'll be able to respond to the poll as we get underway here today, and I'll close the poll when our presenter is ready to begin. Thank you in advance for your participation. PARC is in the business of breakthroughs, practicing open, provide custom R&D services, technology, expertise, best practices, and intellectual property to companies worldwide. 9 Sigma is proud to work with PARC to bring you a gallery on our 9 Sites platform, 9sites.com, where you can view and directly engage with PARC on any of the technologies present on that site. For more information on any of this, please visit the PARC Gallery on our website, or visit the PARC website at www.parc.com. That's PARC.com. Today, Sri Ganesh Madhvanath, PhD, Research Manager, Prescriptive Analytics, will be presenting What Does Today Tell You About Tomorrow? Deriving Actionable Insights Using Predictive and Prescriptive Analytics. In just a few moments, I'll let Sri Ganesh take the floor and present all the fascinating possibilities of this technology. Just a few housekeeping notes before you start. If you have any questions during this session, please at any time submit your questions through the question and answer chat box on your dashboard. We'll be collecting these questions throughout the webinar, and if there's time, we will answer some of those questions during today's webinar, and if not, PARC will follow up with you directly after this webinar. And lastly, I'd like to remind all of you that we are recording this webinar and the content will be available at a later date. Without further hesitation, let me present Sri Ganesh Madhvanath. Sri Ganesh?
Yep. Okay. So the topic for today's webinar, like Jonathan mentioned, is Predictive and Prescriptive Analytics. What does today tell you about tomorrow? Next slide. Next slide, Jonathan.
Just a moment, but Sri Ganesh, we're having a little bit of a technical issue.
Okay.
Let's do that. There we go.
Yeah. So this is the outline for what I'm going to talk about. Initially talk about what we see as data analytics, because this is something that's constantly evolving, as you all know. We'll talk about the approach we take to data analytics here at PARC. And then I'll present some case studies. That's probably the most interesting for this audience. And then I'll summarize, what we have described and talked about during this webinar. Next slide. So the way I look at data analytics is actually in a very broad sense. I think of it as the application of data to any business question or problem that may be informed by that data. And we have arrived at this very broad definition really because of the wide nature of questions and problems customers come to us with. There's a long history of different fields looking at data, but now data analytics has sort of grown to encompass all of those different areas, and that's really the motivation for this very broad definition. Next slide. Now, this is something that, again, some of you may be familiar with. It's a continuum of data analytics domains or problems. Typically, you start with data. You're all familiar with data, the 3 V's or the 5 V's, depending on how many V's you're interested in: variety, volume, velocity, veracity, value, as some people talk about it. But essentially, you have data which can be, biological data. It could be time series data, spatial data, different types of data. You need to extract information, features. Often there is a lot of human intelligence that goes into that step. Integrating multiple data sources, this is where your ETL comes in. And then you have different types of analytics. Descriptive analytics is mostly concerned with visualizing data so that human experts can make some decisions. Predictive analytics tries to answer some specific questions using the data available. And prescriptive tries to go one step further and prescribe some actions that can be taken in response to those predictions. And typically there's a human in the loop because anytime there's something at stake, you want to have a human in the loop. And the idea here is that you can answer business questions and support intelligent business decisions. And you see this pattern in every vertical, in healthcare, transportation, customer care, and so on. And we'll talk about some of these today. Next slide. So at PARC, we think data analytics is a multidisciplinary endeavor because, like I just said, there are many different fields that have been looking at data and trying to use data to solve business problems. And so we look at it as a think tank approach where we have experts with backgrounds in data mining, machine learning, statistical modeling, but also things like dynamic control and systems, operations research, behavioral economics, multimedia analysis, right? And of course, you need big data technologies when your data happens to be big. You may need ethnography to help frame the right questions to ask. And it goes without saying you need domain expertise because normally the questions that come to us are framed in a manner that you need domain expertise to drill down from that to the specific technical questions that we can try to answer. So this is what we mean by a think tank approach. Next slide. I wanted to say something in passing about the nature of models. So in general, the objective of data analytics is to build a model for something that's happening in nature. For instance, you're trying to build a model to predict stock prices, right, from the data that's available. Maybe it's anything from today's weather to stock history, the GDP. So you could have any number of factors, and you're trying to predict a certain outcome. So this is a process that's happening in nature, and you can think of prediction problems broadly as falling into two classes. Classification problems, where you're trying to predict, a certain outcome. For instance, is the stock price going to go up or down? So that's a two-class problem. Regression would be where you're trying to predict the exact value of something. So for example, what is the stock price going to be tomorrow? So those are two broad classes of problems. And when you try to build a model for this process that's happening naturally, you can think of it in terms of a data model. And this is what statisticians normally look at, trying to build a model for the process that's generating the outcome given the input, right? So if you are able to build such a model, then the advantage you have is of interpretability, because you can look at this model and it tells you how the prediction Y is arrived at from the input X. There's another class of models which we can think about as algorithmic models, and these models are really not concerned with trying to model the process that generates the outcome. Rather, they're just saying, let me see if I can figure out the mapping from X to Y. So given a certain set of inputs X, can I predict the outcome Y with a high degree of accuracy? And in some sense, they're saying that the process in nature is just too complex to try and model that. We just try to figure out or try to learn the mapping. And so this involves a certain trade-off or introduces a certain trade-off between interpretability on the one hand and predictive accuracy on the other, because each class of model is really trying to address a different thing. And we will see how in different applications these things are important. Next slide. So let's get directly into some case studies to illustrate some of these ideas. The first domain I want to talk about was prognostics for devices. And as you can imagine, PARC being a Xerox company, Xerox is in the device business. and repair service is one of these foundational processes for Xerox. Some of the research challenges when you talk about low-cost devices is that it's very hard to know when they might fail. The idea here was if you could somehow predict that a device was going to fail, you could actually proactively contact service personnel in the local area and have them go in and do proactive maintenance and prevent the failure from happening in the first place. A lot of the failures with these low-cost devices are soft failures, where it boils down to a customer tolerance for something like print image quality, or avoidable paper jams caused by putting in paper that's the wrong thickness. So it's not the typical kind of failure that you might see. If you go to the next slide, Jonathan, we'll see a typical system which is high capex. So this is a Rolls-Royce engine, and you can see how there are a lot of different sensors here. And these kinds of systems tend to produce continuous streams of sensor data, and you can use a lot of reliability science approaches, time to failure prediction, regression, and forecasting to try and predict when this might fail. But that's very, very different from the scenario we are looking at, where you have a humble office device, and all it's doing is occasionally logging some faults to some kind of a log file. And we are trying to use that to make predictions about device failures. Next slide. So we started out looking at the distribution of service calls across different subsystems and problem types, and we found that really they are very widely distributed across these. And so when we look at what are some really reliable indicators of these failures, we found that only about 10% of service calls could be really predicted using just an analysis of the data. Next slide. So what we ended up doing for this problem is modeling it as a classification problem, where we're trying to predict if there would be a service call within a certain time window. And we use all of the data that we get from the log file to try and make a prediction. So this is an example of a black box classifier, right? An algorithmic model. And with this approach and using a particular classifier called a random forest, we were able to get much better accuracies than we could by just looking at the data. So about 40 to 60% accuracy for the scanner automatic document handler, and more than 80% accuracy for certain part failures. Next slide. So with that, let's get into a much more interesting space, which is healthcare and predicting future adverse events in population health. Next slide. Yeah, so those of you who are familiar with the US healthcare system, you're probably very familiar with the rising cost of healthcare, the aging population, and also new events such as the Affordable Care Act expansion, which has brought many more millions of people into the insured fold. The whole model of healthcare is moving from a fee-for-service model where the insurance company pays the provider for every service that's rendered, to a value-based model where value is defined as the quality of care that's received by the patient divided by the cost of that care. So if you're trying to improve value, it boils down to trying to improve the outcomes and reducing the cost. Next slide. So here we look at two types of adverse events. One is a readmission event. Readmission event is where a patient gets discharged from a hospital and gets readmitted to the hospital within a certain time frame, such as say 30 days. Another one is a visit to an emergency department, which, as you might know, is very expensive. So the idea is that if you can try and predict these kinds of adverse events, you may be able to intervene in time and prevent them from happening. Next slide. The data we had to work on these problems was encounter insurance claims from Medicaid. So for those of you who don't know what an encounter claim is, essentially any time a patient encounters the healthcare system, there is a claim that's generated. It could be for a prescription, it could be for a doctor's visit, for a medical procedure, and so on. And we had 7 years of this data. So some of the features that you can extract from this data that are directly available from the data: demographic information, geographic information, information about diagnosis, procedures, and so on. And then you can also hand engineer certain features based on the available data. For example, counts of different types of encounters. How many times has this patient been to the ED in the last 1 year? That would be an example of feature engineering. And so you can look at these kinds of features, including things like what is the driving distance or the driving time to the nearest emergency room. So these would be examples of hand engineered features. Next slide. So if you take a step back, so now this is the data you have, and what you're trying to predict is really the risk of somebody going to the emergency department. Is it even feasible? When you look at the top causes of ED visits, injuries, these are random events. They may be job related, and really there's very little information we have about these from the claims data. So the claim data has very little predictive power. If you look at substance and alcohol related, we have a little more information because we have maybe information about prescriptions or information about certain tests that were conducted. If you take chronic conditions, that's probably where we have the most predictive power because the condition is chronic, like diabetes, and we have maybe a lot of data on those kinds of things. The other thing to look at is how do you model the problem? If you were to model it as a yes or no problem, will this patient go to the ED visit, to the emergency department in the next 6 months? And then if you look at a specific application, for example, if you're only interested in 10% of the ED population for doing some population analysis, this is something we can try to get high accuracy on. But if you're trying to predict the exact number of ED visits a patient might make in a certain time frame, the healthcare industry calls these frequent flyers. That's a much harder problem because that's a regression problem. And you're now targeting an individual as opposed to a population. Next slide. So we looked at ED risk prediction as the former problem, which is, can we try and make it a Boolean classification problem, a yes or no problem? And that helps us actually deal with some of the noise in the data. We looked at a few different models, and I won't have time to get into the details of these models, but logistic regression is one of those statistical data models which are easy to interpret. Doctors like these models because they very directly tell you the relationship between features and the outcome. We can get better accuracy from a random forest, which is a black box model. Another thing to think about is really thresholds for different applications. So for example, if you're looking at population monitoring, you want low false positives because you want that 10% of the population to be all 100% likely to go into the ED. Whereas if it's case management, you may be interested even if there's a small probability of somebody going to the ED. So this determines the threshold you might set on the confidence that you're getting back or the score you're getting back from these models. So we did extremely well on these, and bear in mind this is claims data. We don't really have clinical data on these patients. Next slide. The other problem that I wanted to touch upon was the readmission problem. And like I mentioned before, this is about trying to predict if the patient might get readmitted into the hospital within a certain time frame, like 30 days. Next slide. So again, we looked at logistic regression. Like I mentioned, the big advantage is interpretability, which is important in the healthcare context. And then what we found was, some of the features that we extracted, or which we found to be relevant, you can see are very intuitive. There's features related to the primary inpatient stay, demographic, previous conditions, and encounter history. And again, the models we were able to build, you can see in this blue band here, that's an accuracy level that's considered acceptable for this particular problem. The LACE ones are things that are used in hospitals today. The XIG ones are the ones that we came up with. As you can see, we are able to get significantly better accuracies. Now, if you look at only the unplanned ones, because the planned readmissions are not very interesting, right? If you're planning to go back into hospital for a particular procedure, the unplanned ones are obviously harder to predict. But even there, you can see, if you try to predict it at the point of discharge, you have a little more information than if you try to predict at the point of admission. And so you can see that small difference in accuracies there. Next slide. So what's next really is getting into some of the drivers, because the model right now is really trying to go directly from some of the features to the outcome. So trying to explicitly model some of the latent or the hidden drivers, which could be things like the health condition, what's happening post-discharge, what kind of community care support the patient is receiving. The advantage of modeling these explicitly is that you may be able to introduce some expert knowledge about some of the drivers for these adverse conditions. Obviously, introducing clinical data into this mix is going to improve accuracy, and I already talked about some new models that can capture the temporal development as opposed to a snapshot in time, and some of these latent or hidden factors. Next slide. So moving on now to a completely different space, which is that of public transportation. One of the problems we were asked to look at was characterizing connectivity. So I'll give you some context on that. So if you take the typical public transit agency, they are interested in growing ridership because that's really key to improving revenues, reducing congestion on roads, and growing their public transit system. Now the question is really, how do existing and potential riders perceive transit, right? How do they perceive transit travel as opposed to the transit agency? Next slide. So this slide gives you a view of the supply side, which is how a transit agency thinks about public transit. They may think about it in terms of spatial measures, such as the network geometry, the number of nodes, the total length of links, and temporal measures such as service frequency, service availability. These are typically available only for individual routes. On the demand side, which is where your consumer is, they think about when do these services actually when are they available, so that can they travel at the desired time, how efficient is the travel, how reliable is the travel. Next slide. So if you were to drill down further into the traveler's view, if you want to get from your home to a particular destination using public transportation, you have to think about the time it takes to walk from where you are to the nearest bus stop, and from the bus stop to your destination, the time that you spend waiting for connections, waiting for the bus, and so on, the actual time you spend traveling, so the in-vehicle travel time, and also the buffer time. So the buffer time is really time that you introduce into your planning as a traveler to account for buses arriving late, right, unscheduled cancellations, and so on and so forth. So this is the traveler's experience of public transportation. Next slide. So we came up with a measure we call generalized trip time, which in a simple way to think about it is really the sum total of all these times we talked about: the in-vehicle time, the transfer times, the waiting times, and the reliability, the reliability buffer time that we spoke about. And we can now think about the connectivity of a bus stop. What is the connectivity of a bus stop? Well, you can think about it as the cumulative opportunity. So if you had 30 minutes, what are the places you could get to from this bus stop? If this is the trip time, the generalized trip time it takes to go from this bus stop to a particular location. The total area that you can travel to is how we define stop level connectivity. And the data we have available is data about stops, routes, service schedules, and schedule adherence at specific time points. Next slide. So we did a field trial in Rochester, where we are, Rochester, New York. And here you can see the picture on the left, it shows the different bus stops you can get to from the bus stop, which is marked in red, right, in a certain period of time. This is, again, using the generalized trip time, and we are assuming 30 minutes at 9 a.m. on a weekday. So it's important to keep in mind that this is going to change at different times of the day because of congestion, where you can get to in 30 minutes will change. The picture on the right in the middle tells you exactly the same information, but if the buses were all to run on time. So the gray dots indicate the additional bus stops you could travel to if the schedules were strictly adhered to. And the picture on the right, the graphs, the plots which are in green and pink, they show the difference between the coverage area if all buses were to travel on time and the coverage area in reality. And you can see there's a 62% difference between these two. Next slide. So now we talked about stop level connectivity. Now, can we extend this notion to talk about the connectivity of the transit network as a whole? And we came up with this idea of a core network. So we only look at those bus stops which have connectivity ratings above a certain threshold. So we can think of these as the well-connected bus stops. And you can see here a plot of all the well-connected bus stops in the light green. And again, the picture is different based on, are we looking at actual services or scheduled services? Next slide. So we came up with this measure of network connectivity, and we found that it's useful for many different things. In a way, it captures the traveler's perspective, the traveler's experience of public transport, because it captures the physical network, that is the available network of bus services. It implicitly captures the service schedule. It captures the reliability of those services as well. And as we've already seen, there's a significant difference when you account for the reliability of the service. We also did some studies to look at the relationship between connectivity and ridership. So if you look at these little zones in this map, those are called transportation analysis zones, and they're based on census data. They're often used for doing this kind of analysis. When we tried to build a probabilistic model to predict ridership, we found that some of the strongest predictors were the population of that zone, the number of workers in that zone, and the average network connectivity within that zone. So you can see how this connectivity measure we came up with can be predictive. And then building on this, we can think about other notions of connectivity, such as what is the connectivity of a city area, what's the connectivity of a city population. And you can imagine how this might be useful for, say, urban planning. If you're trying to set up office space, you may want to set it up in an area with high network connectivity, or you're trying to decide where to buy your next home. Next slide. So let's move on now to the final vertical that I wanted to talk about, which is retail. And we look at a couple of different case studies here. The first one is really customer interest modeling. So this is something that is very important in personalization. So if you're interested in personalizing, it could be a website where a customer comes to read news articles, or it could be product recommendations, a recommender system, or it could be personalized or targeted marketing. In every one of these cases, because you're interested in personalization, you need to build a model of a customer's interests. So the interests in this case may be things like, what are the customer's interests in different types of sports or different types of literature, and so on and so forth. And depending on the problem, you may have different data sources, both private and public, available to you. So for instance, you could have CRM data, you may have email conversations with that customer, you may have call center, chat sessions, web browsing behavior, and social media handles, such as Twitter handles. So the data in general may be structured, it may be unstructured text, images, audio, video, and so on. And though this looks like a rich set of data, in general the data is sparse and it's unbalanced. Next slide. So we looked at a particular data source. Specifically, we looked at Twitter data. So assume you have a customer's Twitter handle. What can you tell about the customer's interests, right? For example, in sports and literature and so on. And for this particular problem, we looked at both the text of the tweets from the customer as well as images that a customer was posting to Twitter. And we used these deep neural networks, which is basically another example of an algorithmic model, a black box model, to extract features from both images as well as from text. And then we map that to a domain taxonomy. So a domain taxonomy in this case may be something like, if you take all kinds of interests, there may be interest specific to sports, specific to literature, specific to entertainment, and so on and so forth. And you can drill down. The taxonomy basically goes several levels deep. And what you're trying to do is figure out, one or more nodes from this taxonomy that the customer is interested in. And that is what our system produces in the form of weighted concept vectors. Next slide. So the output of the system looks something like this. I mean, this is a visualization, but what you can see on the top right is really a set of these interests categories that our system has been able to automatically derive based on the Twitter data coming from this customer. And on the left, you have a visualization which shows, the distribution of the customer's interests between different categories like news, arts, health, society, and culture, and so on and so forth. We can also extract automatically, demographic information related to gender, age, and again, these are all predictions. So they will all come with a certain reliability score. So once you have this interest model, you can then use it for various purposes, such as personalized recommendations for products and so on. Next slide. The second example I want to touch upon was healthy food recommendations. And this is a problem we've started to look at because of the context of obesity. Diet is a major culprit. And we've noticed from our own ethnographic studies that customers are really not able to make much sense of food labels when they go grocery shopping. So our idea was to try and recommend foods to them. Next slide. So the way our system works is actually it mines grocery data, so basically grocery receipts for that customer, and it computes the running averages of pantry staples. It takes this information and maps it to nutrition information. So essentially, it tries to boil that down to what's the vitamins and the protein that this particular customer or this particular grocery shopper actually purchased during this particular time period. It looks at the difference between that and the government recommended daily values of these nutrients, and given that difference or that gap, it tries to recommend healthy food products for that grocery shopper. Next slide. So we looked at multiple approaches for solving this problem, but one I thought might be interesting to share here is how we mapped it to the knapsack problem. Knapsack problem is a very well-known problem in algorithms in optimization. The idea here is that you are a burglar, you have a knapsack of a fixed capacity, and you're trying to burgle a home. You're trying to steal different products or different things that are available in that home. They have associated dollar figures, and there are also certain weights or volumes associated with that. And the idea is to maximize the value of what you steal. the way we mapped it to our case was, you think of the 2,000 calorie diet, the caloric value, as the capacity of the knapsack, and you're trying to really fill that knapsack with the best foods you can so that you maximize the nutritional value of the knapsack. And we try to do this in a way that minimizes the change to the current diet of this particular user, so that the user is not overwhelmed by a completely new diet. Next slide. Yeah, this slide just tells you, a kind of proof of concept we built. So the top part of it is a little dashboard which tells the consumer, what nutrients they're doing well on, what they need to consume less of, what they want to consume more of, and it makes recommendations related to the gaps in nutrition. Next slide. So again, these are just some examples. I could provide many more, but in the interest of I will stop with these examples and summarize some of what we've covered here. So data analytics, like we started out saying, we may think of it as the application of data to any business question or problem that may be informed by that data. The solution to the problem typically depends on the question or the problem itself, and often requires multidisciplinary expertise and tools from different disciplines. The solutions also need to be tailored for the data sources. So whether it's sensor data, it's structured data, it's video data. So depending on that, your solutions are going to look very different. It also depends on the need for predictive accuracy versus interpretability. As we've seen in some domains, we're able to use these black box classifiers like random forest and deep learning, where predictive accuracy is really the most important thing. In other domains, especially in the healthcare domain, interpretability is important, and there we use models like logistic regression, which give us interpretability, but we pay a price in terms of predictive accuracy. So at PARC, we really adopt a multidisciplinary think tank approach. We've seen examples today of statistical modeling in the transportation case, machine learning using random forest and deep learning, optimization in some of the recommender systems, and we looked at examples from very different verticals. We will cover examples from other domains like behavioral economics and dynamic control in future webinars. Thank you.
All right, thank you, Sri Ganesh. Before we get to the question and answer session, we do have a few moments left. I'm going to send out another very quick poll, and while you are all answering that one, I'll provide some feedback to the very first poll question that we led off with. The first poll question was asking whether or not which statement you most aligned with your experience. 70% of you voted, so thank you very much for that. 23% of you agreed with the statement, I have tried previously to use data analytics to solve a problem or understand trends. 12% of you said, I have current data analysis problems that might be understood using data analytics, and 65% of you said that neither one of those statements particularly agreed with you. I'm going to keep the poll open for just a moment or two longer here to give you an opportunity to answer that. Then we will move on to a number of our questions, and hopefully we will be able to provide some feedback as far as the second poll question. We've still got some poll results coming in. I'll keep it open for just a moment or two longer here, and then we'll begin with the question and answer session.
Okay, while we're finishing the poll, I'll go ahead and voice the first question. For the healthcare study on encounter claims, did you have to scrub the data? And was the volume of data overwhelming given 7 years of information?
Yeah, we did have to scrub the data. So, claims data, as you probably know, those of you familiar with that space, there are these codes that are used, the ICD-9 and ICD-10 codes. So a lot of them needed to be scrubbed to extract data. So in fact, a large part of these projects actually goes into understanding the structure of the data and extracting features in the way that we wanted. And so, yeah, that was definitely a big part of it. In terms of the volume, it was, maybe 4 or 5 million records. So that's bordering on big data, but I would not say that was a huge issue for this particular problem. And again, depending on the model of choice, so if you use logistic regression, it's extremely computationally efficient. Other models such as deep learning or random forests are definitely more expensive computationally. Okay.
Okay. Thank you for that, Sri Ganesh. All right, I'm going to go ahead and close that second poll. It looks like everybody that is going to answer has done so. 61% of you responded to that, so again, thank you very much. The options for this particular one asked you what type of data analytics you were most interested in. 50% of you said that you were interested in market data. 60% said you were interested in product data. 45% consumer data. 33% operations data, and 10% said none of the above. We have just a few more minutes here before we wrap up. Have time for maybe one more question from Kevin before we wrap up. So Kevin, if you would please.
Okay. How can we use data analytics for situated design methods and research?
So situated design, if you're thinking about situated display devices in the environment, so maybe I need more clarity on the question. That's something maybe we can take offline directly with the people who asked the question.
All right, very good. We'll answer an additional question. Could you help with some references, like case studies that you've conducted?
Oh, absolutely. Yeah, we have either white papers or academic papers describing almost everything that I talked about today, and we'd be happy to pass those references on.
Okay. All right, I think we're going to hold off there for answering questions. If you have any more questions, please feel free to submit them. We'll keep the webinar open for just a little bit longer to collect those questions. But at this point, that will conclude the webinar. I encourage you to visit the PARC Gallery on 9 sites or visit PARC's website at www.parc.com. That's PARC.com. Quick reminder that this webinar was recorded and will be posted online for viewing later. A transcript of this webinar will also be available. Thank you again for attending, and thank you to Sri Ganesh for his time and his expertise. Have a great afternoon. Please feel free to submit any additional last-minute questions you have to the question and answer box at this time. And